Welcome today for this webinar on 3D IC trends. This is one of the most key technologies, which is on the packaging and manufacturing side, which is basically bringing out the designs which are very very complex designs today. So let's get started. For everyone's benefit, I've copy pasted a form. Please fill this form to get the certificates for this particular webinar. And if someone is having difficulty, I'll be pasting the link again a little bit later in the webinar. So let's get started. So this is the agenda we'll be covering. Why 3D IC and why now? We'll talk about chiplets. We'll also talk about challenges, requirements, and opportunities in 3D IC design. We'll also talk about hot chiplets, some of the recent chiplets which have been designed. We'll also talk about one of the important concepts, which is Introduction to Universal Chiplet Interconnect Express, or also short form known as UCIe, which is an enabling technology for interconnect between chiplets. And then we'll talk about what is the future of this technology moving forward. How do these things are going to move forward? So let's get started. So before I get started, right, I will talk about one of the couple of recent news which happened. Okay, so one is iPhone 16 was released, it with A17 Pro, and iPhone 16 Pro. It was the first device to get TSMC new 3 nanometer silicon, and A17 Pro chip. If you look at how 3 nanometer technology has evolved, it was not as great in terms of performance, right? A17's Pro transistor count bump over A16, which was its predecessor, is pretty modest, right? It was not like it clocked in 19 billion where A16 had 16 billion. So going to next technology level, going to next technology is not bringing in as much improvement, as much benefit as they used to do earlier. And this is an evolving trend, right? As in going into new technology node is becoming more and more expensive. And also, it's not bringing in as much benefit as it used to bring in like 10 years ago or maybe 15 years ago. So this is one of the evolving trend, and this is something which was recently released. In addition to that, there is another event which happened, right? Intel got its chiplets order with the 6th generation of Xeon SPs. This was one of the Intel designs which was done, processor which was done using chiplets. There were separate tiles for cores, memories. There were separate IO chiplets. There were separate compute chiplets. So these are the two news, right? One, your 3 nanometer processor, 3 nanometer A17 processor was not as much as an improvement, even though going to lower technology node. But chiplet based designs gain performance, and these are the recent trends which are happening. Now let's understand how these trends evolved, and everyone like who has been a part of electronics industry has heard about Moore's law, right? Moore's law basically was mainly an economic law. Underlying it was the development of technology, right? It was just a statement, but technology engineers working on it had to make it true by working very hard. And the Moore's law continued to evolve, it continued to serve us, and your technology and the number of transistors doubled every years, and this continued for 50 years until a few years ago where it stopped working. So we now are at a stage, probably we have 3 nanometer and maybe 1 or 2 generations after that. So number of transistors since 1965 have approximately doubled every 2 months. So there was more and more processing power. For example, iPhone, as in this is a well-known folklore which is used, that iPhone had basically more computing power than the NASA's aerospace, which has went into the moon landings. Just to think about as in terms of analogy, if an average family car had seen this much performance increase, and for car it would be speed increase, today we'll be able to travel at the speed of light. So this is also humongous improvement which happened over the years, happened in last 50 years, until it stopped improving that much. iPhone processor I was talking about is a prime example of that. So Moore's law served us for a long time, but maybe we have one or two more generation left. But the technology is not giving as much performance boost as it was giving earlier. While Moore's law was enabling doubling of transistors on a single chip, there is another technology which is often overlooked, was developing. Another trend was evolving, and this was in packaging technology. Packaging technology was also evolving over time, and this is one of the key technology. This is where whole this 3D IC thing which we're going to talk about. What are the trends there? This has one of the packaging is one of the key enabling technology for that. Just to take a pause, I have pasted a link of the form. If you want certificates for this webinar, please fill out this form. And then your certificates will be sent to you in 1 or 2 days. So packaging, while Moore's law was also evolving, it's packaging technology which was often overlooked. It was also evolving. So let's see how packaging technology evolved over multiple years. Initially, we had, as in everyone who has worked in the electronics lab, still people who are hobbyists would have seen these kind of ICs, right? These used to be DIP and SIPs, where you would have basically pins which will go into the board, and you basically will connect using that. Used to be called dual inline package, and it's at some places it's still used. What the limitation with this was the structure, how basically the packaging structure limited how many pins you could have. And package usually was much larger than the die will be very smaller, and there are a lot of pins connected to make it look bigger, because bigger pack for pins you required at least some minimum distance between the pins. And it was similar. SIP was similar to DIP, but it was mostly used for memory module. So DIP used to have only one side of this, and that also used to be typically used for memory module. So this was initial packaging technology developed by Fairchild and the initial companies who were working on microelectronics and IC. Then the new technology, packaging technology came in, which was surface mount. So it solders directly on the top of the board. So like this, it was soldered directly on the top of the board. It was easier, and for machine-based assembly, it was also faster to do this, and it allowed to increase number of pins. There were a few technologies developed over the years for this kind of surface mount: QFP, QoF flat package; PGA, pin grid array; BGA, ball grid array. But because the pin or the pin distance was decreased and it was highly automated, there was increased risk of defects, because pins were very close to each other and very compact. So sometimes because of this pin close distance, the defects could increase for this kind of technology. This, some of you would have seen this kind of, like, one is this pin grid array. You can see the number of pins would be increased. It will be directly surface mounted on the board, or even the ball grid array. You could see that the number of pins which earlier ICs could have, this increased that to many fold from the previous technologies. So then it evolved further, right? Then basically, when more functionality in a smaller space was needed, then there came the need for SoC, system on a chip. Still a single die, but whole system was on a chip. And it was very highly optimized for power, performance, and area. And analog circuits, digital circuits, optical circuits, all the parts of the system were integrated together, and that's why it used to be called system on chip. So it was still a single die packaging, but used to be called system on chip. So basically, we started with dual inline package, quad flat package, small outline package, then other kind of leadless chip carrier. And you can see as we evolved, we packed more and more ICs together, and that also required more functionality. So we had more number of pins evolving until, and this was till 1990s. This around started around 1960s, 1970s, and evolved till 1990s in terms of ball grid array, which we have talked about. And then came the evolution of system on chip. So before system on chip came on board, or around at the same time, the first step toward 2.5D or 3D ICs was something known as multi-chip module. So it used to integrate. So this is still not like still horizontal. Still everything is horizontal, but it used to integrate ICs, also known as chiplets, horizontally on a unified substrate. So there is a unified substrate, and on that all the ICs are integrated and connected. So it offered more functionality, simplified design, and of higher yield, but it was more highly priced at that time than SoC. And but basically it was simpler and easier to make than an SoC. So this technology where you would integrate multiple ICs horizontally on a unifying substrate was evolving also, but it gained prominence in recent few years. Okay. So then came what is known as system in package, and this is still one of the key enabling technologies for even 2.5D and 3D. So in system in package, there was stacking of ICs, stacking of chips, and then wire bond to 2.5 and 3 2. And 3D. And it uses an interposer layer to connect all the devices. It was a simple design for verification, optimized cost and size and performance, does not always need a PCB, and can house all the components if needed. And we're going to talk about this technology a little bit more in detail as part of this webinar. So this is how the packaging technologies evolved. There used to be traditional multi-chip modules, PCB, then a silicon interposer came in, something known as 2.5D technology, and now into fully 3D. So this is how the packaging technology, while Moore's law was doubling the transistors every year, the packaging technology was taking its natural course in terms of evolution and becoming an enabling technology as well. So this is basically, we started at 1970s. There used to be these kind of ICs which you would have seen in your electronics labs with pin-based connection, pin and hole-based connection. Then as the performance requirement, pin connections requirement increased, multiple other technologies came in. We reached at ball grid array here. Then basically SoCs, system in package, package on package, and here and evolved towards 2.5D integrated circuit and 3D integrated circuit. But SoC was like, if you go back 10 years ago, SoC, system on a chip, putting everything, all the system on one IC was still the preferred technology. So what happened? Why did this all change? What is happening is, as we went towards lower end and lower technology, the economic balance has changed. Now, so SoC was basically, or a system on chip was manufacturing a huge number of transistors on the same chip. So basically all the parts, analog part, digital part, all the parts of a chip, multiple system on a chip, putting on the same die or all on the same chip was economically better early on. But compared to that, building smaller dies and packaging them together like kind of multi-chip module or a system in package or something known as heterogeneous integration was less economical than developing an SoC. But as we are going towards lower nodes, this balance has shifted. Going towards lower and lower technologies, it's becoming more expensive for the fabrication. And this balance is now shifting towards enabling technologies where basically you can still get better performance, you can still go more than more, But rather than building a monolithic system together, then doing basically integrating separate ICs and packaging them together using some packaging technology. So this balance has shifted, and that's why we are talking about what is happening in 3D IC. And you would have heard about talk about chiplets. All this is happening because this balance is shifting now. At some For some kind of SoCs, it's already shifted. In addition to that, what one of the trend which you would see, right? AI chips, a lot of AI chips. You would have heard about Chat GPT. All these enabling technologies need specialized kind of chips, specific application chips known as AI chips. And one of the prominent aspect of AI chips is they require huge amount of data. Okay, sometimes the model size can be huge as well, but they require huge amount of data transfer. A lot of time, performance and latency depends a lot on how this data is managed. And one of the key thing is to keep your memory close, because you will be doing a lot of data transfer. It's important to keep your memory close so that you can do this data transfer faster, and that enables faster performance of an AI chip. So simplistic way to think about that is just put DRAM and processor on the same chip on the top of each other, and this is what basically is one of the requirement which is also basically you need 3D technology, 3D ICs or 2.5 IC. In initial years, I would say, as in your performance of an AI chip was limited by compute. What I mean by compute is how much faster you can process. But around 5 years back, 4 years back, you hit a wall, and now memory bottleneck or memory performance is what is making these systems go slow. And this is again one of the key technologies. If you can do an ASIC where basically memory and your compute are very close to each other, they can talk to each other very in a faster manner. That is what is limiting performance, and that's where basically a lot of AI trend is also enabling basically 2.5 and 3D technologies so that you can do a lot of AI operations much faster. And in addition to that, what is also happening is going into a system on chip means, right, as in you are integrating everything on the single chip. That means whether your processor, whether your memory, whether your analog circuits, all have to go to a lower node together. But there are unequal members here, right? As in earlier technologies of going to lower node, it was all equal. But now all members are not equal. A processor, say, for example, may gain more going to a lower node than probably IO, RF, or analog system. And for some analog or RF circuit, it may be impossible to design in FinFET or lower nodes. And the yield stability is another reason. So basically, there is a trend which is going on that basically whatever parts of the chip, not all parts of the chip are equal members. Some parts may actually gain performance or improve while going to lower node, but other parts of the system may actually not benefit and sometimes actually may be worse going to the lower node. Because of that, and there may be stability and yield issues for some kind of these things. Or additionally, some analog or RF, it may not even be possible to go to FinFET or lower nodes. So that is bringing in another change, that maybe not every part of an SoC or every part of the system needs to go into lower node. So this brings into what is known as heterogeneity in the system, that you want different parts of the devices going to lower nodes, and some part may not want to go to lower nodes. So this is also enabling what trend which is happening, which is enabling 3D or 2.5D technology. So, people who want to get certificate for this particular webinar, I have posted a link just again in the chat window. Please fill out that form so that you can get access to, you can get a certificate for this particular webinar. We'll be distributing the certificate in 1 or 2 days. People who are asking a question about recording we'll be putting the recording on our YouTube VLSI Deep Dive YouTube channel. So please, you'll be able to find the recording in a few days on our YouTube channel VLSI Deep Dive. So basically, why 3D IC and why now? You can see multiple trends happening. Moore's law is not giving as much performance boost as it used to. Packaging technology is evolving. Going to lower node is getting costlier. You have specific kind of chips needs, like AI chips needs memory and data to be working in fast collaboration with each other. In addition to that, you also have things like not every member is equal, not every member gets the same level of boost by going to lower technology. So this leads to another a particular term which has been coined, which is known as chiplets. It was also used earlier, but it is now becoming more economical to have small IC design for a particular functionality and connect them together using some kind of technology which we'll be talking about. So these ICs which are perfect in their particular functionality and connect to make whole system are known as chiplets. So basic idea is, let's say, think of this, right, as in you can you if you have a number of menu of modular chips, okay, small chips or chiplets in a library, you assemble these chiplets or chips or ICs together in a package, connect them together using a die to die, which one die to another die using using an interconnect scheme. The chiplet approach is a fast and a less expensive way to assemble various type of third-party chips like IOs, memories, processors. You basically, each of this is a chiplet or a chip which you can connect together using some die to die. This is one separate die, this is separate die, this is separate die, using some die to die interconnect scheme. All these separate dies can be in different nodes. You can see it, for example, DSP is 10 nanometer node, USB is 22 nanometer node, display probably is 12 nanometer node. So connect them together using some kind of substrate or interposer, which we'll talk about, using an interconnect scheme. And it's a fast way to the assemble IP. Each of these heterogeneous IPs can stay, or chiplets can stay in the technology node they're perfect at, and still you be able to connect together. Will be maybe give faster performance and faster more economical from economical from cost point of view. So this is the idea which is developing, and a lot of companies are pushing for it because this gives not only performance and also cost advantages. And we'll talk about some of the hot chiplets which are being developed, or chiplets based design which are being developed. So think of this as kind of high-tech version of Lego blocks, right? And this is something can be a way to extend Moore's law further by allowing for creation of more complex and powerful system, and without having the restriction to having to fit all of these necessary component on a single monolithic chip. Multiple semiconductor companies are already adopting AMD, Intel, Apple, and multiple companies are already adopting this structured chiplet based design, where basically you can take an SoC as a system, basically break it down into smaller logic blocks, or separate it out from kind of functionality like IO and logic, create chiplets, and basically at the back end package them together using some kind of substrate to enable this kind of high monolithic, rather than monolithic, a high performance design. So what are the advantages of doing this, right? The disadvantages which we have talked about, the trends we were talking about, right? You have if you are able to do this, which is now people are able to do this, is there is a flexibility in picking best process nodes for a part. Let's say if your RF works in 28 nanometer best, you pick RF to be working in 28 nanometer. But for a processor, let's say 3 nanometer gives the best performance, you pick the processor in 3 nanometer. So basically it allows you to pick the best process for a part and allows heterogeneity. Improve performance, for example, for specialized processing elements, like which I talked about processor. Similarly, there can be multiply and accumulate unit, which is very, very important for AI chips. You can pick a particular part just get the best performance using a particular processor node. So your performance overall also increases. It is better economics. Your monolithic single SoC chips are becoming too expensive. Going to lower node is becoming too expensive. And as we saw from your Apple's SoC, it may not even be giving as much performance boost as it was being given earlier from moving from a higher performance, higher nodes to lower node. You can have better yields for smaller die sizes. You can a particular chiplet can be done volume manufacturing because it can be used by multiple customers. And since some certain chiplets are already designed, you can your time to market, or you can shorten the IC design cycles as well. So there are certain advantages which come for following this approach. So, and better economics also comes because of this. Of course, there are some challenges as it comes with new kind of technology. It is takes some effort to ensure basically reliability and cost of these chiplets. Important enabling technology for this is the packaging. In addition to that, there is a question of testing coverage since these are chiplets, testing the whole system, DFT, how each chiplet can be connected only with a limited number of pins. The manufacturing process to integrate this is difficult and may require more complex, which we'll talk about. And in addition to that, 3D stacking may introduce reliability issues. So there are also certain challenges also. People are trying to overcome these challenges, and so that they can take advantages of the advantage points we talked about. So let's talk about a little bit, go more detail in terms of this particular technology, chiplet based 3D ICs. Let's understand what are the challenges, what are the requirements, and what are the opportunities in 3D IC design. For everyone's benefit, I have posted a link in the chat. Uh, if you want to get certificate for this particular webinar, please fill out this particular form, and you'll be able to get certificate for this particular webinar in a couple of days. So let's understand, right? So we talked about multi-chip module, right? This was first developed in 1980s. This was also another form of multifunctionalities, and it gave foundries and OSATs design control over their designs. It integrates homogeneous and heterogeneous ICs horizontally, basically onto a unifying substrate. It offered more functionality, simplified design, and higher yield than SoC, but at a higher price at that time. This then basically evolved into system on a chip, where basically whole system was on a single chip. Most components typically of a computer like processor, memories, IOs, DSP, all basically done on a particular system. So it was optimized for power usage, power efficiency. It minimized waste of heat, and it also minimized latency because faster all the parts were on a chip, so faster communication with each other. It was most of the time it was made in foundries and designed by a lot of fabless companies, but it was basically not possible to upgrading or repairing. And it was very common, for example, in mobile computing, like Qualcomm Snapdragon is one of the prime example. Then came system in package, where basically you had stacking of ICs. ICs were connected together using wire bond, or later on something which we'll talk about evolved into 2.5D and 3D. Earlier, basically, they were connected by a wire bond, basically wire connecting from one to another. The new 2.5D to 3D stacking of ICs uses something known as interposer layer, which we'll talk about. This enabled higher density of transistors. Advantages included simple design and verification, low time to market, increased yield, optimized cost, size, and performance. The interposer could have active and passive component. What do we mean by that? We'll also talk about. And it did not always need a PCB, could house all the components which were needed. So the road now, which is evolving from 2.5D to 3D, we started with single die chips, something like this, high performance chips, larger, expensive, more power. Then it evolved into multi chip modules, system on chip, highest performance. Then packaging technologies enabled system in package could include in analog components also. Now let's talk about what is SIP, which is a key enabling technology for 3D IC design, and also talk about what is 2.5D and 3D, which we are talking about. SIP basically enables multiple dies on a common substrate on a single package. And 2.5D and 3D are also SIP in a way, right? So basically it enables multiple dies on a common substrate on a single package. 2.5D introduces what is known as silicon interposer, and basically TSV technology, which we'll talk about. 3D then mounts two or more dies on the top of each other. It also has what is known as active interposer. So let's understand what are these key terms. But key enabling technology for that is system in package. It basically which enables multiple dies together on a common substrate on a single package. Okay. So we used to be SOCs, which were monolithic, basically everything bunched together, a whole system on a single IC. Then 2D and 2.5D integration basically allows multiple ICs or chiplets on different technologies connecting together, but stacked horizontally. Then 3D integration with chiplets also allows them to stack or integrate vertically on the top of each other. So 3D IC is a general umbrella name for a range of manufacturing technologies that enable integrating multiple silicon dies on a single package. So you can have multiple silicon dies, but they are integrated onto a single package. Die placed in 2.5D, these dies placed closely on a connectivity substrate, but horizontally. In 3D technology, stacked, the dies are stacked vertically also on the top of each other. This is built by what is known as wafer on wafer or chip on wafer, and connectivity is done through silicon wires, known as through silicon wires or TSVs, and we'll see an image on that. It can accommodate, this is key part, multiple heterogeneous die like logic, memories, analog. These parts can be in different process nodes. And because of this enables a new level of efficiency, power, and performance, which we are not getting just by taking every parts of an SoC to a lower node. So key enabling technology for this is something known as interposer technology, right? So what is an interposer technology? Okay, it is basically a silicon layer, this particular green layer that you are seeing, a silicon layer between substrate and the die. So these are various dies. This is substrate. So there is something in green that you're saying that is known as interposer. This is basically a silicon layer between substrate and die. So this can be silicon. It can be also be made of glass or other organic substrate. I'm talking about particularly silicon here. So this particular green layer underlying the dies. So it connects dies among each other. So you're using this, basically dies are connected to each other, CPU connected to memory, CPU connected to flash, CPU connected to IO. So these lines that you're seeing, it allows it to connect them. It can also connect to IOs. So it eliminates the need for wire bond. So typically earlier in SIP, if these used to be connected, there used to be wire bonding connecting. So basically a copper wire running along, connecting these input and output pins together. This particular technology known as interposer technology eliminates the need for wire bond. And because of that, is much denser, much more efficient, better, faster connectivity can be done. So think this is basically your silicon interposer. Here you will have multiple different ICs or chips, and they're connecting to each other using basically wires which connect from one IC to another, and also there is vertical connectivity in this. So let's see one more aspect. So this is basically a stepping stone for 2.5D and 3D IC integration. It also uses something known as through silicon wires technology. Okay, think of through silicon wires as a copper pathways that cross silicon vertically. So you are not only connecting horizontally, then you're also connecting vertically. Okay, like this. So you're connecting each IC to each other horizontally, but through silicon wires, you're also connecting vertically. Interposer can be active or passive. The interposer, basically, with the interposer you're seeing, can have basically microelectronic devices in that, or it can just be a connectivity enabler like through silicon wire. So there are both kind of possibilities which exist. Active means this can have specific microelectronic components in the interposer also. If the interposer does not have a microelectronic component, that it's just used for connectivity, it's known as passive interposer. So why interposer, right? So as I talked about, right, as an earlier, these you were connecting all of these together using something known as wire bonds or in IC packaging. Inter, interposer allows this to connect together using basically not wire bond but wire separate technology. So this allows this allows to increase the density of interconnection. You can wire bond will have specific size, specific distance, but interposer technology allows you to have higher density of interconnections. So it's something which enables more than more. Conventional substrate, which you talked about, this, for example, this printed circuit board, cannot support these many pins. This is something interposer technology is not something new. It was has been developed and tested for more than 20 years. But early on, the cost was not worth it. You were getting much better cost advantages. Going to lower node was still expensive, not as prohibitively expensive as it is the case today. So going to lower node was still not that cost. But now as we said, the balance has shifted and it's now resurfaced as one of the key enabling technology. And this particular technology now is giving better performance and becoming more efficient as well. So basically, one of the earliest devices, Vertex, Xilinx Vertex devices used one of the in 2000s, and one of the earlier technology devices using the interposer technology. So as I said, right, there are two kinds of interposer. One is known as active interposer and passive interposer. So passive interposer just acts as an interconnection. So you have tiles, you have interposer. The passive interposer just acts as an interconnection. Of course, as in mechanically, it also holds all the dies together. Communication among the dies, so you have multiple dies, it allows communication among the dies, which are among the dies, the communication happens horizontally. Then vertically also it's connected to do basically connecting to the IOs or outputs world. The connection is done using vertical IOs through silicon wires, TSVs. There are no active devices in the interposer, okay, or in the substrate. So basically this is just used for vertical connectivity and horizontal connectivity, but there are no active or there are no microelectronics parts within the interposer itself. Because this is just used for connectivity, you can have higher wire density. A lot of wires can be connected here without worrying about whether there are any microelectronic devices here. So in passive interposer, it's just used for both horizontal connectivity and vertical connectivity. Through vertical connectivity is done through silicon wires. And basically there is no active device in the substrate, so you get a very high wiring density, and this is the passive interposer. In the active interposer, it only it acts as an interconnection, of course, and holds all the dies together. And communication among the dies in a package, it enables that horizontally and also connects vertically through IOs. But in active interposer, there can be fully functional chips also, for example, IOs, DCs, fast IOs. So active interposer can actually have chip microelectronic devices or sometimes fully functional chips also in the silicon substrate itself, and that is when you have that kind of thing, it is known as active interposer. But because of that, what happens is there are some keep out zones, right? For example, you have this device, so your wire connectivity or TSV connectivity has a keep out zone because they can't be too close to each other. That can impact the functionality or function of these wires. So there your your connectivity will not be as dense as it was in the case of a passive interposer. So there are two kinds of interposers which exist: passive interposer and active interposer. They provide, of course, both horizontal connectivity from one die to another and vertical connectivity through silicon wires. The main difference between them is active interposer will have microelectronics devices within the interposer or substrate also, while the passive interposer will not have. And because of that, active interposer will be having slightly less kind of wiring connectivity density than passive interposer. So interposer again is a key enabling technology for 2.5D and 3D. So let's understand this in a little bit more detail. Before I go there, I will just, for everyone's benefit, I am copy pasting a link. If you want certificate for this particular webinar, please fill out the form on this particular link, and then you will get the certificate for this particular webinar. So in the structure of interposer, basically there are three kind of elements which are there. One is TSVs, which is known as through silicon wires. So through silicon wires are nothing but these yellow vertical bars, okay, across the silicon. So this is going across the silicon. It allows connectivity basically through these through silicon wires. These are typically basically very long and slightly less in horizontal. So the aspect ratio is that it will be longer. Then there is something known as RDL, redistribution layer. This is the very top layer of the interposer. Okay, so this is used for horizontal connection. So this is for lateral communication, and this is used for connecting to the outside, which is through silicon wires. Then there is under bump metallization. Basically, this solder bumps to the package substrate. These are known as under bump metallization. This solders to the bump of package substrate. Let's see a little bit more detail. Through silicon wires are vertical pathways through the silicon interposer. This usually is not straight line. This will be slightly slanted, and because the copper will be filled in, and for it to go through and connect properly, these actually will be slightly slanted or will look like this shape. It has a very high aspect ratio. Width is come, usually very tall. Angle is slightly slanted so as no bubbles when filled with the copper. And in case of active interposer, as we talked about, there'll be keep out zone in active interposer where you cannot create these through silicon wires. Then second is redistribution layer, which basically provides the horizontal pathways along the interposer. You connect one die to another using this horizontal pathway, redistribution layer or RDL, for horizontal connectivity, and your through silicon wires for vertical connectivity. UBM under bump metallization is a thin pad connecting basically the solder bump and the copper in the redistribution layer. It also serves as a barrier to stop the diffusion, and it acts as a mechanical connection. Usually nickel based UBM is widely used. So this is your redistribution bumps which I'm talking about. So basically, you had traditional MCM and PCBs, where basically you had wire bond based kind of connection. Now, basically, your interposer enabled 2.5D by your side by side integration, and then through silicon wires. There can be like if silicon interposer, there can be active interposer, and you can have microelectronic devices in the interposer itself. So the advantage of this was basically if you had a wire bond, it was like it will take more space, connectivity can be limited. Now you have smaller than the traditional kind of packaging. You can have much more connectivity, shorter interconnection. Of course, shorter interconnection then means higher speed, lower power usage, and you can also now do could also now do heterogeneous integration, and it actually does a better heat management, as in 2.5D actually does a better heat management than 3D also. Disadvantages, of course, it was a new technology. It still requires advanced knowledge, harder to integrate, and you basically need to plan in advance, or either take off the shelf CMOS, different processing nodes. So that itself brings its own challenges and better need for heat management techniques. Now it evolved into 3D packaging. Okay, so earlier you were horizontally stacking, and also there was an interposer layer. But what if you can basically stack one IC or one chip over the top of another, and it you use an active interposer? So 3D stacks, basically you have group of dies which are one on the top of another, typically performing the same function. For example, let's say memories may be performing the same function, and it is typically best suited for a particular kind of application specific chip to enable a better functionality. Advantage is now compared to 2.5D, it is even smaller sizes, and not because you are doing now 3D, so it's more than more. It's basically increased functional density. You can think of shorter wiring. You can have this shorter wire when the dies are stacked on the top of one another, reduced interconnect delays, lower power consumption, reduced capacitance, and also allows for heterogeneous SoC design onto different dies. Of course, disadvantages is you have heat management. You have through silicon wires generated stress because there are different kind of layers. Of course, it's very high tech and high design cost. But if you can do it well, then it may perform better than going to lower nodes in the SoC, if you are able to do it. So, but still, 3D IC today is still quite a challenge. From tool and methodologies point of view, there are several point tools which are available, but methodologies are still evolving. You have top level, system level heterogeneous design, planning and optimization which need to be done. In addition to that, these are multiple chiplets connecting with each other. So co-design and doing analysis together is still a challenge in that. And in addition to that, you have doing thermal analysis and multiple other kind of analysis, which is typically done in SoCs today. For example, verification, DFT, connectivity, all these are still challenges from technology point of view. Let's think about some top level challenges, right? You have this whole system with multiple ICs, creating a top level full view, let's say fully optimized netlist, then requirement to validate the connectivity of this, your sign off, like you want to do STA, EMIR, other kind of sign off, that also needs to be 3D aware. Your optimization analysis, your another multiple complex analysis which are done at the top level, for example, thermal analysis, power analysis, routability analysis. The design tool support is evolving, but it's still like bits and pieces. There are point tools which are available, but the methodologies are fully not completely developed and still being developed. There do exist, like from multiple EDA vendors, Cadence, Synopsys, platforms, but it's still an evolving area in terms of making the best use out of it. So top level challenges, for example, like extraction, like layout, parasitics, need to consider TSVs, interposer routing, even for timing and signal integrity. All these analyses need to be 3D aware. As static timing analysis need to take interconnection between multiple chiplets and package and should be able to do all this analysis. Your EMI needs to be handled with multiple die packages, and that may offer less shielding than a single die package. Physical verification needs to handle this 3D stack. What about DRC and LVS on this whole system? What about DFT on this whole system, where the pin, like each of the chiplet pin limits becomes a bottleneck as well? And for example, maybe for TSV, there are additional defects that also itself need to be modeled. So all these challenges do exist. Some of these are evolving, some of these have been solved, but these are the challenges which come in terms of overall flow and methodology because of these 3D and 2.5D IC. So this is one of the source from Synopsys. There do exist solutions. I'm not saying the solutions do not exist, but I'm saying it's still an evolving area. There are bits and pieces different companies doing and on different way. But as it often happens with any new advancements in technology, it's a new trend in semiconductor industry, so it creates opportunities. It can offer compelling power performance and form factor in multiple applications. The cost of SoC development going to lower nodes, which is just increasing, it can help to curb it down. And if the ecosystem evolves, multiple companies, for example, I am an RF company, I can focus, let's say, on 20 nanometer on that particular core strength and get the volumes because different consumers will be using that chiplet. EDA's companies can increase their value proposition by effecting solving the multiple challenges which we talked about. OSAT can become very important for testing and packaging of these 3D IC components, and foundries also. So a lot of opportunities which are also coming up because of these challenges. So let's talk about we talked about the technology. Let's talk about some of the hot chiplets. Like what is actually happening? Who is designing these kind of ICs, 3D ICs? Before I go there, I'm just copy pasting a form. If you want certificate for this particular webinar, please fill out this form. There is a specific question. Can you please explain the interposer layer internals of a design from the layout point of view? This is slightly outside the scope of this particular webinar. This is a short introduction webinar. Probably we can cover that particular question in the later webinar, or we can cover that offline. So please fill out this form, which I've just copy pasted for if you want to get certificates for this particular webinar. So AMD is this is one of the AMD chip. AMD is MI200 accelerator family using these technologies. Consists of two dies joined together with the interconnect of 500 GB per second in what they call infinity fabric. Has separate IO chiplets. It has a stack of 8 stacks of high bandwidth memory, HB memory. So this is one of the AMDs has been one of the leaders in this, enabling this particular technology, making the best use of this technology. First, for example, it was the first multi-die GPU which they had produced. And of course, NVIDIA Hopper GPU, 80 billion transistors. It uses HBM3 interface, 3 terabyte per second memory bandwidth. And as I said, right, for AI chips, memory bandwidth is the key. So that's what NVIDIA enabled using this technology, using these hot chiplets. Intel Ponte Vecchio, 47 chiplets, 100 billion transistors, 5 process nodes, different. There is a compute tile, multi-die package with compute tiles, and with 47 chiplets, 5 different process nodes which were used. So again, one of the SoC which uses this technology to get basically high performance. So now let's talk about one more important thing. We are connecting all these separate dies, right? How are these dies talking to each other? Isn't there, if these different companies are going to produce these chiplets, how are these tiles or chiplets going to talk to each other in an effective manner? Isn't there a need for standardization of these interconnection? So basically, the need, of course, is there is a major strategy shift towards multi-die system. Size of monolithic SoC is becoming too big for manufacturability. Some SoC functionality may require different process nodes for optimal implementation, like we talked about RF. So multi-die system are driving the need for standardized one die to another die interconnect. So standardization is needed in that area. Imagine your multi-die system. It contains one die from one vendor, another die from another vendor. Let's say each of these die is on different process technology. Let's say 7 nanometer and 3 nanometer. You want these dies to interact with one another and seamlessly support For example, let's say the protocols which are industry standard, let's say PCI Express, PCIe, or CXL, among many others. Keep in mind that for each of these die to add to your design, latency is also added in the system, so everything will slow down. Now, making all of this work together with the latencies that will come into the picture requires you to have a standard for these interconnections for these dies. In addition to that, basically, this there are different interconnection technologies which exist. For example, one which exists is PCIe, or PCI Interconnect Express, which is a high-speed serial computer expansion bus standard used for chip-to-chip or board-to-board communication. It has multiple layers, but at a high level, if you think about, there is a physical layer which is closest to the serial link, is tasked with encoding and transmitting packets across the serial link and accepting and decoding packets received. The protocol layer defines the control interaction at a higher level of abstraction. Then there is Compute Expresses Link, CXL. It is built on PCI physical and electrical interface. It also offers cache coherent protocols for maintaining cache coherency between device and system, memory system. There are others also, but at a high level, these two are used. What is UCIe, right? So UCI is Universal Chiplet Interconnect Express. So UCI is a comprehensive specification that can be used immediately as a basis for new design while creating solid foundation for future evaluation. Contrary to the earlier other specification, what UCI does is defines a complete stack for die-to-die interconnect. And it also ensures interoperability of compliant devices, which basically is mandatory for enabling multi-die system. So UCI incorporates features like multiple current and trending use cases which are being used, and it supports all kind of packaging technology. So this is an evolving standard for inter-chiplet connection and the standard for enabling all these chiplet-based interconnection, which is gonna happen. Looking forward, right, what is the future of these kind of technology, right? Getting into lower nodes and designing monolithic SoCs is becoming very expensive. So that's why a lot of companies are adopting it. For example, NVIDIA basically, a lot of companies, AMD, ARM, all basically are supporting these new processor interface. Chiplets of officially, like a lot of, or most of the processor companies are officially believing this is the future of processor design, by which you're going to give performance much more, maybe more than by just going to a lower node. Chiplet and the cloud, for even for AI compute, chiplet and cloud will be the future of enterprise. So this is basically, you will have chiplets coming in not only for the processor kind of devices, data servers, AI compute. So this has a very great future, but of course, with this future, a lot of challenges which we talked about come into the picture. Okay. So this was a very short, high level webinar on 3D IC trends. How did we start from where we were 50 years ago with the Moore's law? How did we end up here? What are the key enabling technologies which are helping us to reach and gain further performance advantages? And this 3D IC manufacturing and also design corresponding to 3D IC has a lot of opportunities and key enabling technologies for next set of designs, whether it's for processors, for AI compute, data servers, in multiple ways.